This is practice midterm number 3, problems 41 through 44 in the Scantron part of the test. And given the following Pauling electronegativities, and I give a table is provided with the element depicted underneath it and the electronegativity entered next to it, and I have the Pauling electronegativities for a group of elements provided. Which statement best describes the following molecules? And option A is a polar molecule. Option B is a nonpolar molecule with polar bonds. And option C is a nonpolar molecule with nonpolar bonds. And so what we're going to do is we can take this approach with a scratch paper. I will go over the scratch paper in a moment and show you, but we'll do these piecewise. What you will do is first, what is the criteria for a polar molecule? Well, a polar molecule is going to require that there are polar bonds, and that these polar bonds have to be arranged in such a way that the bond dipoles add together and give a non-zero resultant, like the same way that vectors would have. And what is the criteria for a polar bond? The criteria for a polar bond is that the electronegativity difference between each bonding pair is greater than 0.4. If it's greater than that, we have a polar bond. So we can use the information provided in the table, along with the molecule drawn with the proper geometry. And with those considerations, we should be able to determine which of these criteria is going to be satisfied. If it's a polar molecule, obviously it has polar bonds. It could be a nonpolar molecule where the geometric arrangement of those polar bonds is such that the dipoles cancel. And then the last option is a nonpolar molecule with nonpolar bonds, which means even regardless of the geometry, there isn't a large enough electronegativity difference between the atoms to give rise to any sort of dipoles on the bonds. So the first one we have to consider is water. So before we go any further, we have to go over and draw it on the scratch paper. And this we've had plenty of practice with, so let's go over and look at the scratch paper. And I've already drawn the water molecule. This won't take you long, and this one you should be able to do in your sleep anyway. And so I've got an electronegativity 2.1 for the hydrogens and 3.5 on the oxygens. Well, 3.5 minus 2.1, that's around 1.4. Much bigger than 0.4. So I have a dipole going this way and a dipole going that way. And if I want to get real technical, I could look at the little lone pair dipoles for the lone pair effect, and they're all pointing in the same direction, which gives rise to an overall, these adding vectorially, gives me a large dipole with water, which pretty much we knew is the quintessential polar molecule anyway, but I just wanted to illustrate the principles so I could answer the first question. So question number 41. What kind of molecule is water? It's a polar molecule. That's option A. So fill in that bubble on your Scantron. Now the next molecule is methane, which we probably knew was going to be nonpolar, but let's verify it. Here I've drawn the methane molecule, and it is with the right tetrahedral geometry, and I have 2.1 and 2.5, which is an electronegativity difference of 0.4, which is less than the minimum amount needed. It has to exceed that before we really would consider a dipole. So regardless of the geometry, this is going to be a nonpolar molecule. But if these were something where there was a difference that was greater than 0.4, and we were having to take the geometric considerations into account, if all of these atoms in the hydrogen's positions are equivalent, for example, fluorine, which would be huge, the geometry would be such that the dipoles would all cancel because they're tetrahedrally disposed. I have one here and one there, and then I've got two here and two there. The dipoles ended up canceling each other out, because this would give a net dipole going this way, and this would give a net dipole going that way. And so they would cancel each other out. So the geometric considerations would be enough. But right now we knew that before we got there, because the electronegativity difference was not substantial enough. So this is a nonpolar molecule with nonpolar bonds. So that is option C. Now for number 43, which is carbon dioxide, we go over and see this is a linear molecule. I have 3.5 and 2.1 and 3.5 again. So this would give rise, I've got around, let me see, 1.4, this is 2.5, sorry. 2.5, 3.5, I've got a dipole going this way and a dipole going this way. So I have definite polar bonds, but you can easily see in this molecule the dipoles are in opposite directions and equal magnitude, so they cancel each other out. And carbon dioxide is a nonpolar molecule. And so it would be, the best description of that would be option B, a nonpolar molecule with polar bonds. So that would be option B. Now, for the last in this particular series, I've got the ammonia molecule, NH3, which we've got over here. This one is, I've got hydrogen, which is 2.1, and nitrogen, which is 3.0. And so that means I've got 0.9 difference. That's large enough to give me a dipole going this way, a dipole directed along each bond. So the geometric arrangements of the dipoles, and let's even take the lone pair into effect, which is pointing in that direction. So all of these dipoles are pointing in this general direction. They add together vectorially to give rise to an observable permanent dipole. So this one is obviously a polar molecule, so that means it's option A. And that completes that series.